Okay, so for part 2 we're going to take a look at p hat. That'll go quick. For p hat estimates the population proportion, just like x bar estimates mu, the population mean. Okay, the distribution of p hat is normal. It has a mean of p and a standard deviation of p 1 minus p over n. The conditions and assumptions for p hat go like this. The first condition is that the population has to be 10 times the sample size. Population size is that's what capital N means. Sample size is little n. So if you have a sample size of 200, you need a population of at least 2,000 that you're drawing from. The second condition is that NP is greater than 10. Sample size times the population proportion is greater than 10. And the third one is that N times 1 minus P is also greater than 10. So these are very easy to verify. You just go ahead and do the math on this side, and when you verified it, put a check mark or something like that that says you verified it. Okay, so that's basically how you do p hat. Now let me show you a couple of examples. So for the first example, let's go ahead and do a sample mean example first. Let's suppose we've got Coke bottles. Okay, Coke bottles or Coke cans are supposed to have a mean of 12 ounces, okay, of Coke in them. Let's say the standard deviation is equal to 0.1 of an ounce. A sample is taken of a 6-pack, so sample size is 6. We measure how much Coke is in each of the cans and we find the average. What is the probability that that average is less than 11.95 ounces? In other words, what's the probability our sample mean is going to be less than what it's supposed to be by 0.05 ounce? Okay, well, if we go ahead and look at the conditions and assumptions, the first one is the population normal or is it not normal? Okay, well, we really don't know. So what I'm going to do is I'm going to assume, just for this problem, that the distribution of ounces in the Coke can is normally distributed. Okay, so I'll just put up here in the problems, assume population is normal. Okay, if that's in the problem, then when I get to the condition, I can say if population is normal, then X bar is normal too. And the assumption that satisfies that condition is that we assumed it was normal in the problem. It was stated up there, so we can say that down here. That means X bar is approximately normal, whose mean is 12, whose standard deviation is 0.1 over square root of 6, and we're looking for the probability that X is less than or equal to 11.95. So if I draw my picture of that, I will get something that looks like this. Okay, and then we'll go ahead and start the calculator up and we can figure out that probability. So we'll start that up. Okay, so now we can look at the probabilities. So second distribution, normal CDF. Our lower bound is going to be a low number, so negative 9999. Our right bound is going to be 11.95. Our mean is 12, and our standard deviation is 0.1 divided by square root of 6, like that. Hit enter, and that's our probability. Basically, it's not going to oh, I see a mistake. That's 11. Should be 11.95. So let me redo that. Let's add an 11 in there. There we go. 11.95. That's better. So that probability, whoops, is going to equal 11.033. So 11.033%. So the chances of us getting a sample mean out of a 6-pack of 11.95 or less is going to be almost 1 in 10, or a little more than 1 in 10, 11%. That's how you answer a question like that. Okay, so now we can do one that's a proportion problem. For a proportion example, let's try this one. Let's say we take a simple random sample of 100 people. Let's say we ask them, who will you vote for in the next election? Obama, or who ran against Obama? McCain. And what we find out from our sample is that the proportion who are going to vote for Obama is, let's say, 45%. Now, the truth, which again is something we probably won't know ever, but let's suppose the truth is actually 50%. Okay, so the proportion who will vote for Obama is 50%. What we find with our sample proportion is that 45% said yes. So this is our estimate. This is the truth. The question is, what's the probability of getting a proportion of at most 45%? So basically finding this sample proportion if this is the real truth. Okay, so again, we can look at the conditions and the assumptions. First condition is that n is greater than 10 times little n. The second condition is that np is greater than 10. The third condition is n times 1 minus p is also greater than 10. And the way we answer them is easy. This one here, we'll just say that there are more than 1,000 voters in the population. Since our sample size was 100, our population must be greater than 1,000, and it is. NP greater than 10, we just plug in what we know. 10, or 100 I mean, times 0.5 is equal to 50, which is greater than 10. So yes, that's correct. And also 100 times 1 minus 0.5 is also 50. That's greater than 10, so that's correct also. So that satisfies our conditions for sample proportions. Therefore, p hat is normally distributed. Its mean is 0.5. Its standard deviation is the square root of 0.5 times 0.5 over 100. And now we can figure out what the probability is. There's our probability statement. Our picture looks like this, 0.5. We're interested in a sample proportion of 45% or less. And so we go to the calculator now, and we say, let me clear that out, normal CDF. Our lower bound is negative big number. Our upper bound is 0.45. Our mean is 0.5. And our standard deviation is the square root of 0.5 times 0.5 divided by 100. And our probability then ends up being, let's see, 1587. So our probability is equal to 0.1587. So what that means is, if this were the case, if the true proportion of people who said they'd vote for Obama is 50%, the probability that we would get a sample proportion for a sample of 100 of 45% or less is actually quite likely. It's almost 16%, so it's about 1 in 6 times. So getting this result isn't really that big a deal from a sample of size of 100 people, even if the proportion, even if the truth is really 50%. So, hope that helps. We'll see you tomorrow.